Francis, for the possibility of being here. And also I would like to start doing some publicity about the Latin America Symposium on Solid State Physics that next year will be held at Bariloche. So if you have the possibility to attend this conference, it will be a very interesting conference. It's the 23rd one in this series of conferences. So, okay, today I will talk to you about something that we have been working during the last years in our lab, about the thermodynamic, structural, and magnetic properties of nanocrystalline vortex matter, and how in this case I will talk to you about the case when the crystallographic orientation of the surface of the samples of nanocrystals of vortices matters in some of these properties. So this work has been done in the low temperature lab of Bariloche, at the Instituto Balseiro of the Atomic National Commission. I also have a position from our National Research Council of Argentina. So my co-workers, this is my team of students. We have a research line on local magnetic and electronic properties in strongly correlated electronic systems, particularly when we decrease the size of the samples. And we use regularly magnetic decoration, local Hawk magnetometry, and we are trying to develop a low temperature and high magnetic field STM. And the work that I am going to discuss with you today was done in collaboration with Moira Dol, a former student from our lab, and now she's a professor at the University of San Luis in Argentina. René Cejas Bolecek, who was my former PhD student. Hernan, Gladys, and Julio, that most of you know, who are researchers at our lab. And also, especially thanks to the generosity of Marcin and Kes that tell us how to use these local Hawk probe magnetometry techniques. So the motivation to study this problem comes from the fact that nanocrystalline condensed matter is now in the spot, because there are a lot of problems in physics in general and also in applications when you have to deal with nanocrystals. Nanocrystals in general are crystals composed of just few particles, hundreds or few hundred particles. And they are composed of some core particles and some, let's say, shell particles, where the binding energy of the particles is smaller, just because they have half neighbors. So the particularities of these nanocrystals in general are that you have a large proportion of particles at the surface with respect to the total amount of particles that you have. And closer. You told me it would not work, but I didn't. Okay, so this problem is interesting for such diverse fields such as chemistry, drug delivery, micro and nano devices, clinical applications, holography, and so on. So, and what we have is, in all these fields are common questions. And these questions are, for instance, what happens with the transition temperatures, with the entropy and the enthalpy, let's say the thermodynamic properties, when the size of the system is depressed. Also, if we can induce some structural phase transitions, and also if the working parameters depend on the crystallographic orientation of the surface of these nanocrystals. Of course, these problems are very important when one is thinking in using these nanocrystals for applications. And we are lucky because in vortex matter we have a model system in which we can reduce the number of particles down to 100 or even less in micron-sized samples. And in our case, we will use this model system of micron-sized samples of bismuth 2212 that is extremely layered material, and therefore we will study what happens with all these thermodynamic magnetic properties when we decrease the size of the nanocrystal of extremely layered vortex matter in this T-wave superconductor. So just to summarize some of our previous results, I will show you here that, for instance, we can do disks like this one. These disks is, for instance, a 40 micrometers disk, and we can generate vortices changing the magnetic field that we apply, and we can image vortex positions by magnetic decorations. And we also did smaller disks of also 20 and 30 micrometers, and we measured the first order phase transition, the low temperature part of the first order phase transition. And we observed that for nanocrystalline vortex matter with only 75 vortices, it means a ratio of surface to volume vortices of 30%. The first order phase transition persists. We observe it as a paramagnetic peak in transmittivity. We measure this with local Hall magnetometry. And then we were able to track the first order transition line when we decrease the system size. These are these circular points here. And we observe that the transition persists on decreasing the system size. And what is more important, that there is no melting point depression. You see these black open points is the position of the melting transition for a macroscopic sample. And the color ones, the green, blue, red, and violet here, are for nanocrystals. And the first order phase transition persists. There is no melting point depression, even in the case where we have an amount of vortices in the surface that is considerable enough as to observe a melting point depression when you compare what happens, for instance, in semiconducting nanocrystals. We also observe that if we evaluate the entropy jump at the transition, there is a depletion of the entropy jump when you decrease the system size. And at that point, we point out that this might be due to two effects that we cannot distinguish up to here. One can be that since it is quite likely that this first order melting transition entails also a decoupling of pancake vortices along the z-axis direction, confinement might be in some way enhancing this decoupling, or it can be also that this depletion of the entropy comes from the fact that the solid vortex phase in nanocrystalline vortex matter is more disordered. So that was what we did afterwards to study what happens Okay. So we studied what happens with the structural properties of vortex nanocrystals when we decrease the system size. And what we observe on going down and down on the disk size from 50 to 40 and to 30 micrometers is that when we observe this amount of density of defects in the macroscopic sample, in a large sample, when in vortex nanocrystals, at the center of the sample, we have more or less the same amount of topological defects, but when we go towards the outer part of the nanocrystal, this density of topological defects increase. Actually, what is clearly seen here, that is an extreme case, is that also the outer shells of the nanocrystals are bending as to mimic the edges of the sample, so there is clearly a confinement effect. And we observe that this excess of topological defects occurs at a distance with respect to the edge of the sample that we call a healing length. So we evaluated this healing length as a function of the size of the nanocrystals and as a function of magnetic field. So what we arrived to the conclusion that nanocrystalline vortex matter is structural more disordered and in the transversal direction than in the case of macroscopic vortex matter. And so we still have the question about what happens about along the vortices direction. this we cannot have this information from this kind of magnetic decoration experiments. It's still an open question, but we know for sure that this depletion of the entropy at the first order transition in parts comes from this disorder. And it's also, this opens a question because we are dealing with a first order phase transition where we have still this entropy jump, unless it's smaller, but we still have this entropy jump. And the order of the solid vortex phase is not so good. It's not, for sure, it's not a Bragg glass-like structure. So it opens the question of which is the symmetry that is broken in this transition, because we are passing from a high temperature phase that is a liquid to a low temperature solid phase that is topologically quite disordered. Well, but now, today, what is new that I am presenting here is how the magnetic properties of this nanocrystal of vortices are affected by reducing the system size. And in particular, this is something that in the case of the first penetration field, this is something that was quite already known, that when you decrease the size of the system, the penetration field increases. Here I show you in red a 20 micrometer disk, and in blue a macroscopic sample. If you do a typical DC magnetization loop with local Hall magnetometry, you observe here the penetration field. It seems like the penetration field of the smaller disk is larger, but if it becomes more clear if what you measure is AC transmittivity. And then you see that there is no transmittivity in the Meissner phase, and as soon as it starts rising the transmittivity is when the first vortex penetrates the sample here. So for the disk, the red curve here, the penetration field is larger than for the macroscopic sample. That is something that was quite known. This is just, I'm showing this here because this will be the way I will have to detect the penetration field, because there are several ways to detect it. So our question was, if the penetration field depends on the crystallographic orientation of the sample edge, because there were some works in the literature suggesting that in the case of a superconductor that has an anisotropic order parameter, and since VISCO has an anisotropic order parameter, or at least in the literature is quite established, it's a relevant question for our problem. So what we have here is what we have done is now not to use disk for these studies, but square samples, cuboids actually, with some tens of micrometers inside and 1 micrometer thickness. So if you zoom in here, okay, this is just a magnetic decoration image of the vortex positions in this 30 micrometer cuboid for an applied field of more or less 20 Gauss. So if you zoom in here with an STM, for instance, what we will observe in a topographic mode is the position of, it's an image of the bismuth oxygen plane, and what you see in blue is bismuth. You don't see oxygen with the STM. And this is the cleaving plane that you obtain when you cleave the sample. And moreover, what you will observe are this supermodulation of the C-axis value, and this helps us to know where are the crystallographic directions here. This supermodulation runs along the B direction, so this should be the A direction. In a schematic representation of the unit cell, this is the A direction. Is a direction that is at 45 degrees of the Cooper oxygen bonds. I make this very clear because in some works it's the other way around. Some people put the A axis at 40 in the direction of the Cooper oxygen bonds. But for me, it will be at 45 degrees. It means that the lattice spacing that I call A is more or less 5.4 angstroms. Along the A direction, as well as along the B direction of the structure, we have nodes in the superconducting order parameter. These nodes have been measured by ARPES. And so when I will have a sample that is oriented in the A direction at the edge, I will call it nodal sample. And when I will have a sample that is oriented at 45 degrees, either from A or B, I will call it antinodal sample. Okay, so what happens, why we think it is important, this crystallographic orientation? Because what happens when we have, well, in the case of an antinodal sample, we will put a magnetic field and screening Meissner currents will appear. If we put a magnetic field like this, as in a conventional S-wave superconductor, screening currents will appear running in this direction and will decay along a distance lambda. But when we and this screening current will depend on the modulus to the square of the superfluid density and on the vector potential. But when we have a surface of the sample that is aligned along the nodal directions, what happens is that we already know that in a distance of the order of c, of course much smaller than lambda, Andreev bound state appears. So therefore, if one goes with an STM tip here, for sure you will not measure a spectra that is like this with a gap, but what you will observe is mostly something like this, that there is a conductance peak at zero bias energy. And these are known as the Andreev surface bound states. And what do these states make to the screening current? Well, these states, when you apply a magnetic field, these states split. And also what happens is that in this direction, when the sample is oriented along the nodal direction, the superfluid density goes to zero, because here the superconducting gap is zero. So it's decreasing in a distant psi with respect to the edge of the sample towards zero. So correspondingly, the supercurrent, the screening current is changing. You have to self-consistently calculate the vector A. So what happens is that at the end, and this is very well explained here, and this reference of the group of Fogelström, what happens is that at the end, the superconducting screening current, okay, it's decreasing in some part of the sample, but close to the edge of the sample, actually, it goes again to zero, because this superfluid density here is going to zero. So what this can be seen, actually, as due to an anomalous Meissner current, because it's like if you had current pointing in this direction here, and the same current pointing in this direction here, but compensated by a current pointing in the another direction. So at the end, what you have is that in this region of the sample, close to, in a distance psi, close to the edge of the sample, there is an anomalous Meissner current, paramagnetic Meissner current running opposite to the original Meissner current. So therefore, you will have a net current that will be smaller or even completely opposite, depending on the material parameters. But it will be smaller in magnitude than the Meissner current that you should be able to measure in an antinodal sample, for instance. So, and this will be important mostly for the Wien-Lewiston barrier. Because we know that when one vortex enters into the sample, here, the Wien-Lewiston barrier acts. So we have a force that tries to pull the vortex out of the sample that is given by the image vortex. This force does not depend on this Meissner current that we have here. But we have also the force that is pulling the vortex inside, that is the force that is made, the electromagnetic force that is made by this net surface current. So if this current is smaller, the force to push the vortex inside is smaller, and therefore you should need to increase the field in order for this vortex to penetrate. So the immediate consequence will be that the immediate consequence will be that the penetration field will increase. So this was predicted theoretically in a work in the group of Schoppel. And actually, they observed that the ratio between the nodal and antinodal penetration field has this evolution as a function of temperature. So what we did, and I will go very quickly because I don't have too much time, is we preparated samples in a process that combines electron beam lithography and physical milling, and we end up with samples that have between 20 and, well, hundreds of millimeters in size, in diameter or inside of the square. And one, after cleaving these towers that you see there, they have 1 micrometer thickness. And we prepared these samples using masks that were aligned along the nodal direction of the sample, because first we measure where runs the A vector, the A unit cell in our sample with X-ray, regular X-ray. So we align the sample with the edge of the squares in the nodal or in the antinodal direction. Those will be my nodal or antinodal samples. And then we place these samples in local Hall magnetometers with 16 times 16 micrometer square working areas. And we have nodal samples with different sizes, and antinodal, 2 different antinodal samples. Of course, we have nodal and antinodal samples of the same size. We apply a magnetic field perpendicular to the samples, an AC and a DC magnetic field, and we measure the magnetization in DC measurements and the transmittivity in AC measurements. And what we observe is that either in DC or in AC measurements, the penetration field of the nodal samples is enhanced. For instance, here, this is the result for the 50 micrometer squares. In red, I show you the data for the nodal samples, and in blue for the antinodal samples. And you can see clearly that the transmittivity evolves from 0 at larger fields for the case of the nodal samples. We measure this for different temperatures, and we obtain these curves. So here you see the results of the penetration field as a function of temperature for 50 micrometer squares. In red in the nodal direction, in blue in the antinodal direction. We have 2 samples in the antinodal direction, 1 sample in the nodal. Open symbols are coming from DC data and full symbols from AC data. And it's quite clear that the penetration field in the nodal case is enhanced. And moreover, at very low temperatures, well, not so low, but the difference is of the order of 70%. And so one can wonder if this difference can come from differences in the size of the sample, because I told you that the penetration field depends on the size of the samples. When you decrease the size of the sample, it increases. So what we did was to measure, in the case of nodal sample, how does change at the same temperature the penetration field when you change the sample from 20 to 50 micrometers, so 2.5 times. And this change is much smaller, it's 18%. So what I just showed you before cannot be accounted for a difference in the size of the sample. No, probably there is some influence of the geometrical barrier, but since the samples have more or less the same size, I would say that it is quite likely due to the difference in the Beam-Livingston barrier for the penetration of vortices. So then what we did was to compare our data with the theory, and the agreement is quite good within the error, within the experimental error. Here I'm showing in orange our data. We have 2 sets of data because we had 2 antinodal samples to compare and 1 nodal. And this was the theoretical prediction. So it is quite in good agreement with these calculations. And so also I show you here that the dependence of the penetration field for different sizes of the sample follows a square root of T over D dependence, which is consistent with the Beam-Livingston expression. As at a fixed temperature, it depends as the square root of the thickness divided the typical longitudinal size. Of course, there should be some influence of the geometrical barriers, but it seems to be quite dominated by the Beam-Livingston barriers. And so, summarizing, because I don't have too much time, what I show you is that the first order transition persists for vortex nanocrystal with less than 100 vortices, that there is no melting point depression as it should be expected for such a small amount of particles of vortices in the system, that there is there is a depletion of the entropy jump at the transition, and also the solid nanocrystalline vortex phase is more disordered than the macrocrystalline samples. And so this opens up the question on which is the symmetry that is broken at the HFOT transition. It does not seem to be a transversal symmetry on the structural properties of the vortex lattice. And what I show you today that is completely new is that also the penetration field is dependent on the crystallographic orientation of the vortex structure. So I thank you for your patient and long attention. And I thank you especially to Dimitri for his schematic explanation on the anomalous Meissner current.
Well, we have